What's up, guys, and welcome to another USACO problem. Today we're going to be doing the USACO 2018 February contest silver problem, problem 1, rest stops. Okay, so we have Farmer John and his personal trainer, Bessie, are hiking up Mount Vancouver. The mountain is a straight trail with length L meters. Farmer John will hike the trail at a constant rate of RF seconds per meter. Notice it's not meters per second, it's seconds per meter. This actually makes it easier for us. Anyways. And Bessie's gonna be um, RB seconds per meter. Okay. But we also have a bunch of rest stops along the way, right? And there's also grass on the rest stops. There are N rest stops. Each of the rest stops is xi meters away from the start of the trail, and it's obviously less than L because L is like the finish point, and has a tastiness value of ci. So if Bessie rests at stop I for t seconds, she receives ci times t tastiness units. Okay, so I guess you can go into the rest stops, you can rest for a few seconds, and you can get some fresh grass. Okay. Um, Bessie would like to maximize her consumptions of tasty grass, but she is also worried about Farmer John, and she thinks that if any point along the hike she's behind Farmer John, he might lose all motivation to continue. Okay, so that just means that Bessie has to be always in front or just or the same distance from the start as Farmer John. So she cannot never be behind Farmer John. Okay, and it also says that Farmer John's gonna be slower than Bessie, which makes sense. And also notice that all of the rest stops are distinct, so there can't be two rest stops at the same position. Okay, this is an interesting problem. Let's go to the whiteboard. All right, so for the sample case over here, we have RF equals 4. So this represents 4 seconds per meter. RB equals 3, which means 3 seconds per meter. And Bessie's going to be faster. And there are two rest stops over here. One at 7 with a tastiness value, I think, of 2. And one at 8 with a tastiness value of 1. Okay, and the optimal solution for this problem is actually going to be we're actually going to go to both of these rest stops, and we're going to first stop at this one, and then we're going to go to this one. So let's see how that plays out. So I'm Bessie, right? The red one is Bessie, and this color is going to be Farmer John. Okay, so I guess first it's going to go to this rest stop over here. So let's just calculate how long it takes Bessie to go to this rest stop. So as you can see, we need to travel 7 meters to get there. So let me erase Bessie over here and then place Bessie over here. So we traveled 7 meters, and we know it's 3 seconds per meter. So how long it takes Bessie to go to 7? It's going to be 3 times 7. 3 times 7 is 21. So it's going to take 21 seconds for Bessie. We're going to say Bessie to travel over here, right? So let's calculate how long it takes Farmer John to travel here. Actually, let's just calculate how much Farmer John will travel in 21 seconds. So that is 21 seconds divided by 4, which is around a little bit greater than 5. So we'll just put Farmer John is going to be like right here. Okay, great. So we don't need to know the exact position, but Farmer John's somewhere over here, and Bessie has already came to number 7. Okay, so what Bessie's gonna do now is Bessie's gonna wait until Farmer John catches up. So Farmer John's gonna catch up, right? And for every second that Farmer John moves, that Bessie doesn't move, Bessie gets a tastiness value of 2. So Bessie's satisfaction value, I forgot what it is, but it increases by 2 for every second that she's not moving and Farmer John is moving. Okay, so how long is that? So well, we can figure this out by calculating how long it takes Farmer John to travel to number 7, right? So let's just do that for now. So Farmer John Okay, so he travels 4 seconds per meter, and there are 7 meters to travel, so it's going to be 4 times 7, which is 28. Okay, so Farmer John's going to take 28 seconds, and Bessie is going to take 21 seconds. Okay, so there's like a 7 second in between, right? So during these 7 seconds, Bessie doesn't move. So that's going to be 7 times 2, which is 14. So our answer is going to increment by 14. Okay, so by that time, the satisfaction is 14. So we can just erase this. And now they're at the same spot. Okay, so now there's one more step, which is there's one more rest stop. I mean that Bessie needs to go to. So it's this one over here at 8. For Bessie, it's gonna take 3 seconds. For Farmer John, it's gonna take 4 seconds. So Bessie's gonna actually wait 1 second. So 1 times 1, we can just do this. 1 times 1 is 1, right? So in other words, when Bessie is here, Farmer John is somewhere like over here, right? And after one more second, Farmer John's gonna catch up to Bessie. And they're gonna be both over here. Now what happens after this? Well, nothing much happens after this because the finish line is right here. The finish line is at 10. And there are no rest stops in between. So I guess Bessie just finishes and then Farmer John finishes. We don't really have to play that out, but you get the idea. So with this example, we have 14 and then we got one more, so we have a total of 50. Okay. Okay, so interesting. So some of you might be a little bit confused, because when you look at this problem for the first time, right, you can see that there are many ways that Bessie could have chosen um, to stop at the rest stops, right? So Bessie could have actually stopped here for a bit and moved on to 1 before Farmer John catches up, right? And then stop at 1 for like a little bit. And so you might be thinking brute force is not going to work. It's just not. Because we have just way too many rest stops. First of all, it's 10 to the power of 6 meters. And then we have like 10 to the power of 5 rest stops. That's already like a lot of combinations that you can do. So we probably won't be using brute force for this problem. But how do we actually solve this? And to solve this, you need to make a pretty important observation. So you just need to make one observation, and you should be able to solve this. But to make that observation, we need more examples. So right now I've added 3 and 5 over here as rest stops. Our RF and the RB are going to stay the same. So if you look at this, right? Would if you were Bessie, would you go to like 2 and 1 and ignore the ones with 3 and 5? Probably not, right? Because the 3 and 5 are greater values than 2 and 1. And for every single second that you rest, you get more tastiness units if you stop at 3 or 5. So you don't really want to stop at 2 and 1. But why? Why don't you want to stop at 2 and 1? Well, you can make the argument that, okay, so there's one thing. It's that when you stop at, there's only one benefit when you stop at 2, right? You get more time. So when you already come all the way over here, Farmer John is probably only like over here. And so you get a little bit more time to rest, right? Whereas if you stopped at 5, right, you're over here, but Farmer John is pretty close behind because this distance is smaller. So you're going to get, a little bit less time. But it's more tastiness value. So which one is the right answer? Does tastiness units are tastiness units worth more, or is time worth more? And so you can think about this question, and it seems like, there's not really a solution to this unless you try everything. But if we just ignore this 2 and 1 over here, and we just look at the 3 and 5, right? So how do I? So if I wanted to go to 5, should I stop at 3 first, or should I go straight to 5? Well, if you calculated this out, you would say that you wanted to go straight to 5, right? See, what happens when I go straight to 5 is I need to take 4 steps, right? So that's 4 times 3 is 12. And that is Bessie. For Farmer John, it's going to be taking 4 times 4, which is 16. And that's a difference of 4. So the waiting time is going to be 4. Okay, so and then, well, obviously our answer is going to be 4 times 5, which is 20. Okay, so what happens when we go to 3 and then go to 5? So when we go to 3, it's going to be, when we go to the rest stop with a tastiness value of 3, but we actually go 2 steps. So that's 2 times 3 is 6, and then 2 times 4 is 8. So we wait 2. So I'm just going to write down here. So we wait 2, but then our tastings value is 3. And over here is pretty much the same, right? We have to go walk 2 times. We're again going to wait 2 because 2 times 3 is 6, and then 2 times 4 is 8, so it's going to wait 2. So this is going to be 6, but the next over here, when we make that transition, it's going to be 2 times 5, which is 10. Okay, and you're going to get 10 plus 6, 16. So as you can see, if we just went straight to 5, we got something like, we got 20, right? We went 0 to 3, and then 3 to 5. So this is just making 2 steps here. We got what? We got 16. So it's better to go straight to 5. But can you see why? Well, the reason is that the wait time is actually the exact same. So it doesn't matter how many stops I make. When I go to 5, the wait time is going to be exactly the same. So we can see the wait time is 4 if I go straight to 5. And the wait time is also 4. We waited 2 from here. We waited 2. And then we waited 2 once more. So that's 4. Okay? So as you can see, the wait time is the same. And what do we do with the wait time? We multiply it by the tastiness value we get, right? So in this case, we multiplied 2 by 3. And then we multiplied the 2 by 5. But in this case, in the first case, right? Bro, I did? No, I didn't mess up. Okay, I was like, I messed up. No. For we multiply the wait time by the 5, by only 5. So we want to multiply it by only 5 instead of multiplying by 3 and 5, right? So we want to go, in other words, we want to go to the greater value. Okay, so we've been looking at only the 3 and 5 over here. Let's look at everything now. So now that we have an understanding, let's look at everything. So we have 3, 5, 2, 1. So here is the question again, right? Should we go to 5 first and then go to 2? Or should we directly go to 2? Well, if you think about it, the wait time is the same. If we jumped from 0 to 5, or 0 to 4 in this case, and then jump from 4 to 7, it's the same thing as going straight to 7. Right? It's the same wait time. So the only thing that matters is the tastiness value. Okay? So what we want to do 2 times the wait time. Or do we want to do 5 times the wait times part of the wait time? We'll just call it wait A plus 2 times wait B. And you know that wait A plus wait B is just going to be wait. It's going to be the same time. So if you simplify this, right, you're going to get that this one is always more optimal since we have this 5 over here. Pause the video if you need to think about that. So the answer to the question is that we have to go to this 5 first, and then we go to this 2. Okay? Because 5 is the most tastiest value, and then we go to 2, it's always going to be better than if we just skip to 2. Okay, so at this point, you might be able to think of kind of like the solution. The solution is going to be a greedy solution, right? So when I start over here, I'm looking in front of me, and I see 3, 5, 2, 1. Okay, I want to go to 5, right? Because it's the most tastiest value. So let's go to 5. And then after 5, I see 2 and 1. So it doesn't really matter that I see 1 and 2, or if I see 2 and 1. It's always going to be the same because I always want to go to the one with higher tastiness value. Okay, so I want to go to 2. Okay, what happens after 2? When I'm at 2, I look in front of me and I just see 1. Well, it's a rest stop, so that's better than no rest stop, right? So we go to 1. So this is going to be the path that we travel. And it's always going to be the most optimal path if we always choose the one with the greatest tastiness value. And that is the whole solution of this problem. So I know I didn't take too long explaining the proof behind this, but I think if you made a few examples to yourself, you would see why this holds true. So let's look at the code for this problem. Okay, so we have ln rf rb, and actually, when you write this up, you're gonna see that L is completely useless. Like, we never use it anyways. So I don't know why they included it, but okay. So we have N is the number of rest stops, RF is Farmer John, and RB is Bessie's speed. Okay, so my strategy here is kind of like sort the rest stops, right? But I actually do a little bit of a different approach. So in C++, there's pair of int, right? I'm going to use that, right? But I'm going to change the input a little bit. So instead of storing it like how they did it, which is what? They did xi and then ci. So instead of storing it as xi and ci, I want to sort it by the cost or the tastiness value first. So I want to put c here. And then I do this negative x because I want the cost to be greatest. I also want it to be closest to me. Right? Because if they're the same, I would want something, obviously want to go to something close to me first because I have more options. If I go to something farther away from me, I might skip a few options. So I want to do that. So we're going to do a reverse sort. So it's using this grader over here. But why do I do the negative x? Is that because if I don't do the negative x, right, if the costs are the same, it's going to sort the x by descending. So that means greater x is going to come first. I don't want that. So I want to reverse the opposite of that. So I just use negative x. And all I have to do is I have to reverse it when I look at it again next time. So we go in, we actually get the second first because the second represents the x and it gives us the x first. So we do the second and then we do the first and then we reverse the second. So it stores this cost and the negative x. Okay, we sort it, we reverse sort it. We have this answer over here and the current position of both. So the answer is going to be in long because it's going to be pretty large. And the position actually represents Bessie and Farmer John's position because when Bessie goes, Farmer John has to it has to wait until Farmer John fully follows. You can make a proof. I think there's a proof that you have to the most optimal solution waits for Farmer John to come all the way to Bessie first before moving again. You can probably prove it to yourself, but I think it's pretty obvious why that is if you just use the method that I said over here. But let's keep going. So we go through the rests, and obviously the ones with bigger cost is going to come in the front. And we unpack the x and c according to this row over here. If the x is smaller than the position we're currently on, that means the rest stop is behind us. We can't see that, so we just continue. Okay, and then we get this distance, which is x minus the position. It's pretty self-explanatory. How many meters I need to travel to get to that rest stop? Okay, so now we do a little bit of calculation, which is what we did on the whiteboard. We say d times rf minus d times rb, which is how after that gives us, how many seconds we need to wait after we get to that rest stop, multiplied by the c, which is the tastiness value of that rest stop. Okay, then we just add that, and then we set the position to the x, which is to the rest stop. And then, yeah, that's it. We go through all of them, and then we just print the answer. Again, this is pretty straightforward. And yeah, that is about it for the problem. The coding is actually very very simple. I guess there's a little bit of trick with the c and the minus x, but you can get around that, right? Using other methods. But I think the most important part of this problem is definitely seeing the rule or the greedy rule that you must go to the rest stop with the greatest taste value, no matter if it's close or far from you, right? And how do you find that? Well, we said over here, one most important thing is that the wait times are exactly the same. If I go directly there, my wait time is 4. If I stop first and then I go there, the wait time is also 4. So when the wait times are the same, you just want to maximize the tastiness values. Okay, so I would say this is somewhat like a medium um, type of problem. But yeah, I hope you guys enjoyed, and I'll see you in the next USACO problem.